Hello everyone, welcome back. We're going to jump into 5.2, which is properties of rational exponents and radicals. And this is kind of like almost two lessons in one, with this could be its own lesson itself, just the rational exponents, and radicals could be a different lesson, but we're all together here in one, so I hope this is not too long. We're going to be using the properties as we talked about before in class with these both exponents and the radicals. Before we do that, let's just look at a little cartoon. So here we have the teacher at the top saying, well, here we go again. Did anyone here not eat his or her homework on the way to school? So if you're not familiar with Far Side, that's a Far Side cartoon. Alright, so those core concepts are really important, and this one specifically here we're going to need to know. We talked about this in class, so you got to really kind of focus on remembering when to do what on these exponents. So here's the situation where we add the exponents. Here's the situation when we multiply the exponents. On this one, we're going to be kind of distributing the exponent into both of the parts of the product in here. Here's on this negative exponent, you could say I put it already over 1. Anytime you want to change a negative exponent to a positive exponent, you just got to change its location. So if it's in the numerator like it is here, you'd change it to the denominator and it would change to a positive exponent. If it was a negative in the denominator, you could change it to the numerator and it would change to a positive exponent. So basically, if you take a power and move it from the numerator to denominator or denominator to numerator, it just changes signs on the exponent. Here's one we need to remember. That's an easy one, but often forgotten. Anything to the 0 power is 1. A lot of times people think it's 0. It's not. The quotient of powers, here's where the situation we subtract the exponents, and on this one we're going to give the exponent to both the numerator and the denominator. And I would take a little bit of time there. You can stop the video and just look at those examples on the other side. Here's some from the book. I'll just quickly put that out there, so if you want to look at these examples too, you can stop the video and look at those also as well. But we're going to jump into the extra practice, which starts on page 131. So you want to make sure you're on page 131 to start doing problems 1 through 4 in the extra practice. Okay, so number 1, we're using the properties here to simplify the expression. And with this one, it looks like it's one of those, the product of a power, or right here we have a product on the inside, or a power of a product, it might be called. So we have this product here, and so you could take this 1 negative 1/3 and give it to both of these separately and do it that way, that's okay. But here's a little trick here. Since these are the same exponent in here, the 3's are both there for the exponent, you actually can just multiply the 2 times the 3 right now. And so we can do that, 2 times 3 and then to the 3rd power. So that might be a little easier, in fact. And then we're going to raise it to that negative 1/3 on the outside. So I'm just going to put brackets around that. And our negative 1/3 on the outside now. So this will give us a 6 to the 3rd power underneath there. So 6 to the 3rd. And now I'm going to cross cancel the 3's there from our exponent, because we're going to multiply these exponents. It's a power of a power situation. So that now just gives us our 6 to a negative 1 exponent. And that's now the fraction going to turn into a fraction, because this is kind of like a numerator. So it's got to go down to the denominator. And it leaves an empty space on the top of the fraction. We always want to fill that in with 1. So 1 over 6 is our answer, just a 1/6 on that one. So the 6 goes at the bottom, becomes a positive 1 exponent, leaves this empty space on the top. You always want to fill that in with 1. On this one's got the quotient here of some powers. Each of these would be powers, 10 to the 1st power. I put a 1 there just to show that that is a power of 1. And since they have the same base, we can subtract these exponents. So it's going to be the base 10, and then I'm going to change 1 into 5 over 5, so it has the common denominator of 5. And it's going to be minus a negative. I'm going to change that to a positive. It's going to be a double negative, changing to positive here, then the 4/5. So 5 over 5 plus 4 over 5 is what it becomes. We're not adding the exponents. We really are subtracting the exponents, but it's 1 minus this, so minus a negative 4/5 becomes a positive, double negative. And so now we have 5 plus 4 for the top numbers of this fraction. That's going to be 9/5. Our answer then is just the 10 to the 9/5 power. So 10 to the 9/5 power is our answer on 2. For 3, here's another one where you might think, okay, I'm going to take this 1/6, give it to the numerator, give it to the denominator, and you definitely could and wouldn't be wrong doing that. But notice that the exponents inside here are both 5s. So just like number 1, we can just divide 52 over 4 and then raise it to the 5th power. And that might be, again, like a little easier there. So 52 over 4 to the 5th power. And then we'll have this 1/6 power. I'm going to put the brackets and then the 1/6 on the outside of that. So 52 over 4 is 13. So we're going to get 13 to the 5th power on the inside here. And now that's a power of a power situation. We're going to multiply the 5 and the 1/6. Multiply the exponents. 5 times 1/6 is 5/6, so it's just a 13 to a 5/6 power. That's how we can leave our answer, simplified form. Then number 4, this one's got a big fraction here. What we have is actually really kind of 2 problems in one. We want to do the problem on the top, this product first, and then we'll do the quotient, which would be the fraction. So the first thing is we would like to get this number 3 also over here. We'd like to change the 27 to a 3. And when you're working with exponents, you can do that as long as you have 3 to some power will give you 27. And we should know that 3 to the 3rd power is 27. So we can change the 27 to a 3 to the 3rd power here. And then we would actually multiply. So this would be like 3 to the 3rd power and then raising it also to the 2 over 3. So we're going to multiply these. So it's like a power of a power situation. You can cross cancel the 3's. And now that leaves you with 3 squared. So this right here really is the same thing as saying 3 squared. Well, we like to, as we add our exponents, we would like that to be common denominator with the 1/3. So I'm going to change the 2 into a fraction. So we're going to say 3 to the 1/3 times, instead of saying 3 squared here, I'm going to say 3 to the 6 over 3, because 6 divided by 3 would be 2, because remember this really is 3 squared here now. And so now I can add these exponents on top. But now we have this bottom part. This bottom part, what we want to do here is really kind of turn this back into a radical to try to figure out what this is down here. So we're going to see that we could also, eventually subtract exponents, but I think it might be easier just to figure out what this is. So if I put this into a form like this and see, does this actually give us something simpler? Because we're going to have the 8 be the radicand underneath. The 3 is our index. The denominator is always the index or the root. And then that 4 is the extra exponent that you raise it to afterwards. So is this a perfect number? And it is. The cube root of 8 really is 2. And we're going to see that's going to be 2 to the 4th now. So when we do the top part, we add these exponents here. 1 plus 6 gives us 7 on the top. So 3 to the 7/3 power. This is now going to be 2 to the 4th on the bottom, as we're kind of doing this separately. And 2 to the 4th is just a number. It is 16. So the best answer here is this answer, 3 to the 7/3 over 16. All right, let's move on to number 5. And problem 5, we want to find the simplest expression for the perimeter and area for the given figure. So this given figure is a square, as you can tell. They're all the same side, the sides are all the same, and the angles are all the same. So that definitely is a square. So first of all, the perimeter, of a square, to find the perimeter of the square, you can add up all the sides, but since we just know one side and they're all the same, we really can just do this. The perimeter is going to be 4 times the side length. And so as we plug that in, it's 4 times our side length, which is the 10x to the 1/4, and then we just multiply 4 times 10. We don't do anything with the exponent. We're not going to multiply 4 times 1/4 at all. It's just 4 times 10, just the big numbers multiplied to give us 40. So the perimeter there is just 40x to a 1/4 power. For the area, to find the area of a square, you would just multiply the side times the side. So it's basically multiplying this times itself, or side squared. Area equals side squared. And that's what we're going to do here. Plug it in. Here's our side. We're going to square it. So now this one, there is 2 parts to this 10x to the 1/4. The 10 is one part. The x to the 1/4 is the other part. We need to see this really as a product here. 10 times the 1/4. So we're going to raise the 10 to the 2nd power, and then we're also going to raise the x to the 1/4 to the 2nd power. So as we do 10 to the 1 to the 2nd, that's 100. And then we're going to multiply these powers here, which will give us 2/4, and we'll simplify 2/4 to a 1/2. So our area will be 100x to a 1/2 power. That's our answer for area on that one. Okay, shifting gears a little bit, we're looking at properties of radicals now. We talked about these in class a little bit as well, so just kind of review this a little bit. Look at these examples as we're moving forward. So you can stop the video real quick and look at those, or just look at them in your notes. Here's a couple from the book. These are examples from the book, and you can maybe pause it as well here and take a look at those real quick before moving forward. Oops. Okay, so 6 through 8, we're using those properties of the radicals to now simplify these expressions. So we talked about this before. If you have the same radical, you can multiply what's underneath these radicals. They're both sixth roots, so you can multiply 25 times 625. That's going to give us 15,625. And now we want to figure out, okay, is this something I can simplify here? Is this a perfect sixth root? Possibly it is. Maybe it's not. So we could figure that out and try some numbers. I would try 5 first of all, because obviously 2 can't go into this. 4 is probably not going to go. This ends with a 5, so I would try 5 first and see if I multiply 5 times itself 6 times. We can use our calculator for this. 5 times itself 6 times, will it give me that number? So 5 times 5, and 3 times, here's 4 times, 5, 6 times, and it does give me that number. So I know that this is a perfect sixth root, and that the sixth root of this number is 5. So our answer for that is just 5. And this one, since these are both square roots, we can make this one big square root and then do the division. We can divide here. And like I said, these are square roots. You can write the number 2 in there if you want to, if that helps you, but you don't have to. If you see it there with nothing, you just know it's a square root. So one big square root with 343 divided by 7. You can do that real quick there on your calculator, and that's going to give you 49. And we know the square root of 49, that's 7. So our answer for this one is just equal to 7. Here's another one where we have kind of 2 problems in one. So we want to do the product on top, and then we have a quotient to do. So the product here on top, we can put this together. They're both cube roots, so 25 times 10, that's going to give us 250. And then we'll have the bottom part there, the cube root of 2. Since these are also both cube roots here, we can make this into one big cube root and divide 250 by 2. So 250 divided by 2 is 125, and now we just have the cube root of 125, which we can know that that should be 5. The cube root of 125 is always 5. So that's our answer, is 5. Okay, take a little break here, look at a joke of the day. What did the bee say to the flower? What did the bee say to the flower? Well, it's going to say, "Hello, honey." All right, moving on to our next part. Now we're going to do some vocabulary. So page 130 on your vocabulary, so you want to turn back to that. Simplest form. So on simplest form, what we need to write down for simplest form are really just these 3 things. That's why I marked this off here. So this is what you want to write on page 130 for simplest form. And you may want to write some of these parts here if it helps you, but definitely these 3 bullet points. So what is simplest form of a radical? Well, first of all, no radicands have perfect nth powers as factors other than 1. So you can see the word radicand in here, and I wrote this over here. The radicand is just always the number underneath the radical. That's what it's talking about when it says radicand. So basically, this would be the situation. You might have a cube root of 24. And is that simplified? And you got to think, well, what are my perfect cubes? You know, and we can look at our pink chart. Our pink chart here. Let me find it. There it is. So our pink chart. This is on the board in the class. And we want to see our perfect cube roots here. 1, 8, 27, 64. Those are the perfect cubed roots here. So in 24, can any of these numbers go into 24? So obviously 1, we wouldn't use 1 because that can go in everything. That really doesn't matter. So the first one really to look at is 8. Can 8 go into 24? And yes, it can 3 times. So that tells you this is not reduced yet. This is not in simplest form because there's still a perfect cube root in that number 24. So that's what we're talking about. The next one, bullet point, no radicands can contain fractions. So it's like this situation. You have a radical and then you have a fraction under the radical. That is not okay. You cannot have a fraction under the radical, mainly because the denominator cannot be under the radical. Here's another one that's very similar. No radicals appear in the denominator of a fraction. So it might be like this situation, 1 over the square root of something, or some radical of something. That is also not okay. You cannot have a radical in the bottom of a fraction, whether it's like this or like this. And I wrote this down over here that this is okay. It's okay for the radical to be in the numerator, just not in the denominator. So we can have this be simplified form, but these are not okay to be in simplified form. And here's a couple more problems from the book. You can kind of just take a look at these. If you want to pause the video and take a look at these two examples, you can. But we're going to move forward and look at the next part on your extra practice. I think we're on page 132 now in your notes. Actually, here's another one that's going to be on 132, so you might want to take a look at this one as well. Here's another example from the book that we're going to get into on page 132. Okay, so 9 and 10 we're asked to write in the simplest form of this radical, so we want to use those kind of 3 bullet points to kind of go off of as to what's simplest form. So this is really that first one where you can't have any, it's already one radical here, it can't have any still perfect 7th roots, and this one's a 7th root here in here. So we need to figure out, okay, what are the perfect 7th roots? On our chart I didn't go down to the 7th roots. I got, you can see the 6th powers, or the 6th roots are there. We could see that 2 to the 6th power is 64. So we could start by looking at some of those. One, we can think of 1 to the 7th power, that's always going to be 1. 1 to anything is going to be 1. But then 2 to the 7th power is 128. If 2 to the 6th is 64, then 64 times another 2 will give us 128. So that's really the first number to check. We would want to check to see, can this go into 384 evenly? And so we can just, on our calculator, do 384, let's clear that there, 384 divided by the 128 to see, does that go in evenly? And it does go 3 times. So we know that this is a perfect 7th root that's in this number here. So we're going to say 128 times 3, and then we're going to see, okay, what's the 7th root of a 128? Well, that's just 2. So 2 is going to come out with the 7th root of 3 still left. So that's what our answer is going to be, 2 7th root of 3. On number 10, here's one where it's got a fraction under the radical, and again, that's not okay, because it can never have, the denominator can never be under the radical in any way. So what we need to do is try to figure out how to rationalize this and make it a rational number at the bottom. So since it's a cube root, we want to look at kind of our cube roots over here, our perfect cube roots. And 9's the number we're going to use. Which cube root can 9 go into out of these perfect ones? So obviously we wouldn't use 1. It's not big enough to go into 8, so it can't go into 8. It does go into 27. That's the one we want to use then. 9 will go into 27 exactly 3 times, so which means we need to multiply 9 times 3 to give us a 27 at the bottom, which that'll be a perfect cube root, making it into 3. So here's what we're going to do. We're going to do a process called rationalizing the denominator. And that's where I'm going to multiply the top and bottom by a form of 1, and that form of 1 is just going to be the same thing over itself. And like I said, I have to multiply this by 3, so I'm going to multiply by the cube root of 3 on the top and the cube root of 3 on the bottom. That makes 1. Anything over itself is 1, so I'm not changing the value of this, just changing the form. So when I multiply this, this is called rationalizing the denominator. Rationalize the denominator is that process of taking this into a rational number. So now we can multiply underneath the 5 and the 3 and the 9 and the 3. So we'll do that. 5 times 3 is 15. So we got the cube root of 15 on top, the cube root of 27 now on the bottom. And now this cube root of 27 becomes a nice rational number for us of 3. So cube root of 15 on the top over 3. Now, even though that 3 could go into 15, we cannot reduce those numbers because that's underneath the radical and that one's not. And we would leave it like this. It's okay to leave it with the radical on the top, just never on the bottom. All right, go back to page 130 real quick for your vocabulary on the word conjugate. So this word conjugate here, the best thing to do is just to write down and copy down this part right here that I highlighted and circled. this is the conjugate. Basically, it's exactly the same thing, just the opposite sign. So a square root of b plus c squared of d. The conjugate of that would be a squared of b minus c squared of d. It's just the opposite. We talked about conjugates back when we were doing complex numbers as well. But this is a conjugate here. It just goes back and forth. The conjugate of this is this one. The conjugate of this is this one. So we're going to use that to help us rationalize these denominators. As you can see, number 11 has a radical in the bottom, which is not okay. So we got to use a conjugate of this now to rationalize this. The conjugate of 4 minus square root of 5 is 4 plus square root of 5. I'm going to put that on the top, and I'm going to put that on the bottom. Because again, we have to multiply by a form of 1. That's anything over itself. So as I multiply this by this conjugate, 1 times this will just be what that is, 4 plus square root of 5 on the top. But as I multiply these down here, we're going to do the sum and difference pattern. So the sum and difference pattern, this is a sum and difference. Here's the difference, here's the sum. We can just do the F and L from FOIL. So the first terms, 4 times 4 is 16, so that's going to multiply. The negative times positive will be a negative sign there in the middle, and then the square root of 5 times another square root of 5, we can multiply those and get square root of 25. So that's the sum and difference pattern where we just multiply the F and the L from FOIL. And now as we simplify this 16 minus the square root of 25 will actually be 16 minus 5. So we can realize that. That's going to become an 11 at the bottom of our fraction now, and there's our answer. 4 plus square root of 5 over 11. Number 12, the same kind of thing. You may want to pause the video and try this one on your own, or you can just keep watching and going with me. So we need to multiply by the conjugate. So this conjugate of the 1 plus square root of 6 is going to be 1 minus square root of 6. We're going to put that on the top and put that on the bottom. As we multiply the top, we're going to distribute this square root of 2 into here. So the square root of 2 times 1 is going to give us the square root of 2. We'll have a minus sign. And then the square root of 2 times square root of 6 will be the square root of 12. We will multiply the 2 and the 6 because they're under the same radical. So it gives us the square root of 12. At the bottom here, we're doing the sum and difference pattern. So 1 times 1 for those first ones. The positive times negative is the negative sign. Square root of 6 times square root of 6 for the last ones is square root of 36. So now as we start to get our answer here, we're going to put the square root of 2 here on the top minus. This square root of 12 actually can be reduced. This is not in simplest form, and we'd always want it to be in simplest form in our answer. So think about what perfect square could go into 12. What number is a perfect square that could go into 12? Like, 1 we wouldn't use, but 4 can go into 12. So we could change this. I'll just put it over here. The square root of 12 can become 4 times 3, where 4 is the perfect square, and the square root of 4 is 2. So that's just going to give us a 2 square root of 3 then, as the simplest form for the square root of 12. So we need to change that over here in our answer to 2 square root of 3 to be in simplest form. Down below, 1 minus the square root of 36. Well, this is really 6 here, so it's going to be 1 minus 6 at the bottom, and that's just going to give us a negative 5. So you can have your answer this way. With this negative 5 down here, if you want to move the negative instead of leaving it with the 5, you can move in front of the whole entire fraction. That's another way you might see the answer sometimes. Okay, so we're on the home stretch here. So if you go back to 130 one more time, just write down one more vocabulary word, which is for like radicals. And what you want to write down for like radicals is what I underlined here. Radical expressions with the same index and radicand are like radicals. And I just reminded you that index is the root that's outside here, radicand is the number underneath there. So like radicals will have the same index and they'll have the same radicand. And here's a few here. You can kind of look at these real quick if you want to. You can pause the video and look more at those from the book. These are examples from the book. Okay, so here's our last 4 problems. We're writing in simplest form, so we're going to use the like radicals kind of definition to help us with these. So here's like radicals on 13. They have the same index, both cube roots, and they have the same radicand, both 5s, which means we can just put those together, negative 2 plus 40 in front. And so that's just going to give us, take 2 away from 40, that's going to give us 38 in front. So 38 is in the cube root of 5. That's all that was. Very simple one. On number 14, though, this one's got the fraction exponents on this. We would want to change that to radicals. So both of these can change into radicals. This is going to be fourth roots because the denominators are 4, so the indexes are 4. We don't have to worry about the 1s because that's not going to do anything to that. These are our radicands here that are in the parentheses, so it can change to this. So 2's on the outside of a fourth root of the 1250 minus 5's outside of a fourth root of 32. And now since they have the same index but they don't have the same radicand, we would want to try to get them to become the same radicand to be able to put these together. So first of all, I know that since they're both even, 2 can go into both of those. So I'm going to start with 2 and just divide each of these by 2 and see what I get. When I start with this one, 1250 divided by 2, that is 625. And we want to look at our fourth roots, so here you can look at our fourth roots over here on our pink chart. Fourth roots is 625 is one of the perfect fourth ones. It's 5. So I can change that now to a 5 here with a fourth root of 2. So now that will become this right here. So the 2 times 5, so this 2 is now going to multiply our 5 with the fourth root of 2. These numbers up front will now multiply. The big numbers multiply. We already had the 2 there, but now this became a 5 that we're going to multiply the 2 with. This one over here with the square root of 32, again we're going to see, okay, 32 divided by 2, that we should know pretty well, is 16. The fourth root of 16, again we can kind of maybe check this over here and see that we got fourth root of 16, there it is. It is 2. So this will become 2. We're going to multiply the 5 times a 2 on this one. And 5 times 2, and then we still have our fourth root of 2. So now you can see they're like radicals with the same index, the same radicand. 2 times 5, and both of these will give us 10, so we're going to get 10 fourth root of 2 there, minus another 10 fourth root of 2. So 10 minus 10 basically is just going to give us 0. So our answer on that one is 0. And 15, here's another one where we have kind of 2 problems in one. We want to do the problem on top, the product first, then we can deal with the quotient. And so we want to put these together first. They are the same radical. We're multiplying here, so we can multiply what's underneath, the x times the 18x. So that's going to give us, oops, that's not what I wanted to do. Sorry, I showed that too soon. Actually, I want to write on this one. So for this one, we're going to start with the fourth root of, this becomes a fourth root, that's a 4, 81x squared. And it's over the fourth root of this 16 to the x to the 36. Okay? So at that point, we can kind of simplify things a little bit here. We can see that we got, this can become one big fourth root now, because they're both fourth roots. We can do 81x squared over the 16x to the 36. And the only thing I can reduce here, I can't reduce the numbers, but I can reduce the x's. So I can cancel these x's out here. These 2 can cancel out with 2 of these. So 36 now becomes 34. And so now what we can see here is fourth root of 81 and a fourth root of 16. Is that on my chart? So look at our fourth roots again. It is. The fourth root of 81 is a 3. The fourth root of 16 is a 2. So those can become numbers right there. So I can kind of do this now. There's my pen. So I can, sorry about that with the bell. I try to avoid those if I can. So this is now going to become, actually not a fourth root anymore. That becomes a number. So on the top, we're going to see this just become a number. It's going to be, what do we say this was? The fourth root, that's a 3 on the top we said. Fourth root of 81. This is now going to become a fourth root of 16 is 2, so that can become a 2 at the bottom. But we still have all these x's, 34 of them in fact. So we need to realize that for basically on a fourth root of an x. So if I have a fourth root here and x to the fourth, that's going to give me 1x. Because they're both 4s. So for every 4 x's I have underneath of a fourth root, I'm going to be able to take out 1x. Well, how many times does 4 go into 34? So that would be 8 times. That would give us 32, right? So basically now I could say 8 x's can come out. and I take 32 away from this, there's 2 x's left. So there's 2 x's still left underneath this. This is a fourth root of x squared. Problem is I have a radical at the bottom of my fraction. Remember, we said that's not okay. So let's quickly just rationalize that. How many more x's do I need to give to this to make it where it's like this? Well, I need it to become 4, so I need to give 2 more x's. So I'm going to be doing this here, x squared over x squared. So the fourth root of an x squared over x squared, that will now add 2 more x's here. So when we actually multiply the top of this, we're going to get an answer now of 3 with the fourth root of an x squared on top. That's our numerator. Let me get rid of this. We don't need this in our answer. That was just me showing you and explaining. And then 2 is down here, and now we're going to add 1 more x to the 8, so it's going to be x to the 9th power. See, these radicals now go away because now the x squared and x squared make that x to the 4th, which allows me to give 1 more x out to this x to the 8th, making it x to the 9th. So that's now our answer here. There's our final answer on that one. Okay, last problem. But it is a doozy. There's 4 different things here that we're going to put together. Our constant numbers here, the x's, the y's, and the z's. So let's start with just the constant numbers. We got to get them together on the same level. So they're either going to be on the top or going to be on the bottom. So since this is a negative exponent here, let's take this and move it to the top. And so it'll be a 21 times a 7 to the positive 1 power, so just times 7. So that's going to be on our top. The x's, here's a negative 32 or a negative 3 over 2. That's going to go down below to become positive. This right now down here is x to a 1/2. This square root of x, the root is 2, so that's the denominator, and there's no extra exponent, so it's just a 1 on top. So x to the 1/2 is going to just be that square root of x. We're going to multiply that now times this one. It's going to move to the bottom. So it's x to a positive 3 over 2. It changes signs when you move it from one level to the other. As far as the y's, here's a negative 1, so we want to move this one to the top to match up with this one. Again, this is going to be a 1/2 exponent for y. So on the top, we're going to see a 1/2 exponent there for this one, times this is moving to the top, so it's also a positive 1/2 exponent. And now as far as the z's, they are both positive exponents. This would be a positive 1. So we want to move the one that's smaller. 5 over 2 is bigger than 1, so we want to move this one to the top. So we're going to see z to a 5 over 2 on the top. And we're going to multiply that times z. Let's make this 1 into 2 over 2. But since I'm moving it to the top, it has to change signs to a negative 1, so it's actually going to be negative 2 over 2. That way our denominators are the same when we put them together. So the only thing at the bottom is the x's at this point. So as we multiply 21 times 7, that's on the top, that's 147. So that's the part of the top here. We're going to add the exponents on every single one of these here. So 1/2 plus 1/2 is just 1. So y to the first is just going to be y. This is going to be adding these, which really 5 plus a negative 2 is going to just be 5 minus 2, which is going to give us z to a 3 over 2 exponent. And down below here, we're going to add these. This is a 1/2. So 1 plus 3 is 4 over 2, and 4 over 2 is actually just going to give us an x squared at the bottom. So that's a 4 over 2 exponent, but we want to reduce it to x squared. So the only thing that we may change here, I think this is a fine answer, that's okay, but the book actually changes this z part a little bit here. Let me just show you what the answer showed in the book. It said that that was the same, but when they got to the z's here, this was the same too. It said that you could put z square root of z. Now the reason why they did that is because of this. If I did this, if I just change this here and put z underneath, 2 is my root. I don't really need that, but I'll put it there just in case you can see it. 3 is the exponent for the z underneath. You can always do that. It's the extra exponent, or it can go also underneath. So for every 2 z's, we can pull 1 out. So we can pull 1 z out, which leaves 1 z left underneath that square root. That's why they're saying you can do that. Alright, so that concludes our lesson for 5.2, and you're ready for now the assignment for 5.2. I'll see you later.